You believe the world around you is solid. You touch objects. You feel surfaces. You sit on chairs, hold your phone, and walk on the ground. Everything about your daily experience tells you that matter is real, solid, and tangible. But physics says something shocking. You have never actually touched anything in your entire life. Not once. Right now your hand might be resting on a table. It feels solid. Your brain interprets it as direct contact. But at the microscopic level, something completely different is happening. Your atoms never actually meet the atoms of the table. Instead, the electrons surrounding the atoms in your hand repel the electrons surrounding the atoms in the surface. Electromagnetic forces push them apart. Your hand never reaches the table. There is always a tiny gap. What you feel as touch is not physical contact. It is the sensation created by invisible electromagnetic forces pushing particles away from each other. In other words, the solid world you experience is more like an interaction between force fields than physical objects colliding. And that is just the beginning. Because the deeper physics goes, the stranger reality becomes. When people hear the words quantum physics, they usually imagine something very small. Tiny particles, tiny atoms, a microscopic universe hidden beneath the visible one. But that idea is misleading. The quantum world is not a tiny place somewhere far away. It is the fundamental layer of reality itself. Everything you see is governed by quantum mechanics. The air you breathe, the light entering your eyes, your body, your brain, even the chemical reactions inside your cells. All of it follows the strange rules of quantum physics. The classical world we experience every day is simply the large-scale result of countless quantum interactions happening underneath. In other words, the quantum world is not separate from our reality. It is the deeper structure that makes reality possible. For decades, science textbooks described atoms using a simple analogy. If an atom were the size of a football stadium, the nucleus would be a tiny grain of sand in the center. Electrons would orbit far away. Everything in between would be empty space. But modern physics has revealed something even more surprising. According to quantum field theory, the universe is not made of particles at all. Instead, it is made of fields. Invisible fields exist everywhere in space. Particles are simply vibrations or excitations within those fields. An electron is not a tiny solid object. It is a localized vibration in the electron field. A photon is a vibration in the electromagnetic field. Matter itself is not made of little billiard balls. It is made of patterns of energy moving through fields that fill the universe. This means your body is not a collection of solid objects. It is a constantly shifting pattern of interacting fields, a dynamic structure of energy. And what you perceive as solidity is really just the result of those fields interacting. One of the most misunderstood ideas in quantum physics is the so-called observer effect. You may have heard claims that consciousness creates reality, that the universe only exists when someone looks at it. But the real physics is more subtle. In quantum mechanics, observation does not require a conscious mind. It simply means interaction. When a quantum system interacts with another system, information about its state becomes defined. For example, when a particle interacts with a photon of light, another particle, or a measuring instrument, its possible states collapse into a specific outcome. This process is known as decoherence. Before interaction, a particle may exist in a superposition of possibilities. After interaction, one outcome becomes reality. This means the universe is constantly updating itself through interactions between systems. Reality is not static. It is a continuous process where probabilities resolve into actual events. Perhaps the strangest phenomenon in quantum physics is something called entanglement. When two particles interact in certain ways, they can become linked. Their quantum states become connected. Even if the particles later move far apart, that connection remains. If the state of one particle changes, the other responds instantly, no matter how far away it is. Experiments have confirmed this behavior many times. Particles separated by large distances still behave as parts of a single system. Albert Einstein once called this spooky action at a distance, because it seems to challenge our intuitive idea that objects are separate. But modern experiments have repeatedly confirmed that entanglement is real. It suggests that at the deepest level, The universe behaves less like a collection of independent objects and more like a single interconnected system. Before quantum physics, scientists believed the universe was perfectly predictable. This idea came from classical mechanics. If you knew the exact position and motion of every particle in the universe, you could calculate the entire future. This concept was famously described as Laplace's demon, a hypothetical intelligence that could predict everything. Quantum mechanics destroyed that idea. At the smallest scales, nature is fundamentally probabilistic. Particles do not have definite positions or properties until interactions occur. Instead, they exist as probability distributions, a cloud of possible outcomes. When a measurement happens, one possibility becomes reality. But which one will occur cannot be predicted with certainty. Only probabilities can be calculated. The future, therefore, is not fixed. It is a landscape of possibilities. Another strange phenomenon is called quantum tunneling. In classical physics, if a particle does not have enough energy to cross a barrier, it stops. Imagine throwing a ball at a wall. If it does not have enough energy, it simply bounces back. But in quantum physics, particles behave differently. Sometimes they appear on the other side of the barrier. Even when they do not have enough energy to cross it, they tunnel through. This sounds impossible, but it happens constantly throughout the universe. In fact, quantum tunneling is essential for the existence of stars. The nuclear fusion that powers the sun relies on particles tunneling through energy barriers. Without quantum tunneling, stars would not shine. The universe would look completely different. Even processes inside your own body, such as certain chemical reactions, rely on tunneling effects. Reality allows events that classical physics would consider impossible. All of this raises a fascinating question. If reality is so strange at the quantum level, why does the world appear so simple to us? One possible answer comes from evolutionary biology. Our senses did not evolve to reveal the true nature of reality. They evolved to help us survive. Think of your computer desktop. You see icons, folders, buttons. But those icons are not the real data. They are simplified symbols that allow you to interact with complex processes happening inside the computer. Our perception may work the same way. The colors, shapes, and solid objects we experience are like icons on the desktop of reality, a simplified interface designed by evolution. The true underlying structure of the universe is far more complex. Quantum experiments also challenge our intuitive idea of time. In everyday life, time seems to flow from past to future. But some quantum experiments suggest the story may be more complicated. In delayed choice experiments, the way a particle behaved in the past can appear to depend on measurements performed later. These results do not mean we can change the past, but they do suggest that at the quantum level, the relationship between past, present, and future may not be as simple as we imagine. Instead of a single timeline, reality may behave more like a network of correlations connecting events. All these discoveries point toward a radical possibility. Maybe the universe is not made of objects at all. Instead, it may be made of relationships. This idea is known as relational quantum mechanics. In this view, properties like position, motion, or energy do not exist independently. They exist only relative to other systems. A particle does not have a definite state by itself. Its properties emerge through interactions. Reality, therefore, is not a collection of isolated things. It is a vast network of relationships and interactions, a web of connections stretching across the universe. So what is the quantum world really like? It is not a hidden microscopic universe beneath reality. It is the deeper structure of the reality you already live in. A world where particles behave like fields, where certainty becomes probability, where separation becomes connection, and where solid matter becomes patterns of energy interacting through invisible forces. The quantum world is not somewhere far away. It is the invisible architecture of everything you experience, including you.